Section 3. Fundamentals of Deep RL, Policy Gradient Methods. Utilizing policy gradient methods. In policy gradient methods, we update the policy directly. We parameterize the policy and perform updates on the policy parameters, seeking to improve the policy. This is in contrast to Sections 1 and 2, where we learned estimates of the state or action values. Then we extracted a policy based on those values, like we did with epsilon greeting. The picture on the right has a view of value-based and policy-based methods and how they intersect. Many deep RL algorithms combine value and policy-based methods, like reinforced baselines and actor-critic, which we'll discuss later in this section. Some benefits of policy gradients are that they allow stochastic policies, i.e., can behave according to a policy distribution rather than act deterministically, can work well in continuous action spaces, often have better convergence than value function methods, and can make solving some problems easier. There are two formulas that I've highlighted on this slide. The first is the general overview of the policy gradient method. We parameterize a policy with theta and some performance measure j of theta. We seek to improve j of theta by gradient descent using the step size alpha. The policy gradient theorem is how j of theta is typically expressed as the gradient of the log probability, in this case denoted by policy pi based on state S and action A, multiplied by some quantity q, which scores how well the policy performed. The gradient log pi part of the formula is a policy gradient and will be in every method we discuss this section. Where the methods differ is in how we define the q part of the formula. We'll be using the reinforce algorithm in the code for this video. For the q function that we mentioned in the last slide, reinforce uses the reward collected during that episode. The reinforce agent will act until the end of the episode, collecting a trajectory of experience. At the end of the episode, for each step in the trajectory, reinforce will perform a gradient descent update on the policy, multiplied by the discounted reward returned from that point forward. Since it uses episode returns, it is a high variance method, and since it uses actual returns, there is no bias. Methods that use a value function to estimate returns generally reduce the variance while introducing an acceptable amount of bias. PG methods can work in discrete and continuous action spaces. The DQ1 method we went over in Section 2 required discrete action spaces, i.e. a limited number of actions. Continuous action spaces are often parameterized by a probability distribution, and we learn the parameters of the distribution. For example, we can assume the actions come from a normal distribution and try to learn the mean and standard deviation of that normal distribution that leads to the best policy. TRFL has functions for both discrete and continuous policy gradients. TRFL usage follows the three basic steps. We set up the tensor and the policy network in the graph. We input the output of the policy network and placeholders for actions and values into TRFL.discrete policy gradients. In reinforce, the values placeholder is from the trajectory of rewards. In this session, we run the optimizer to train on the policy gradient loss. TRFL also has the function TRFL.discrete policy gradient loss, which wraps discrete policy gradient, allowing the input to be multiple discrete actions. Policy logits is the output of the policy network as mentioned in last slide. The action values depend on the type of policy gradient method used. This value can be a value function estimate or, as in our reinforced case, the discounted reward trajectory. Usage for continuous action spaces for TRFL.policy gradient is similar to the discrete case. The main difference is the first argument is a policy distribution in the continuous case. We parameterize the policy distribution rather than producing policy logits. For example, if we parameterize a normal distribution, we'd find values from mean and standard deviation that produce a good policy. Scan discounted sum is a convenient function for handling sequences of rewards and discounts. We use it in the code for this video to apply discounts to a trajectory of rewards, as in the pseudocode seen here. For TRFL usage, we set up the placeholders for the sequence of rewards, the sequence of discounts, and the initial value of the sequence. Then in the session, we feed the reward, discount, and initial values trajectories into a feed dictionary for the TRFL tensor. The return is the discounted sequence and the initial value, discounted by the decay parameter. Reverse changes the order in which the sum is done. Let's look at some code. In the notebook is an example of lunar lander. As mentioned before, we guide the spaceship down between the flags. In policy gradients, we parameterize the policy directly. Here's an example of that by setting up a policy network. This is the discrete case for using TRFL.discrete policy gradient. The first input is the policy logits from the policy network. Then we have the actions from the placeholder. And the last input is the values. In this case, we're using reinforce. So the value placeholder will be the reward trajectory. Another thing to note is that when we take actions with the policy gradient method, we use the self.actionProb tensor setup here. This takes the policy logits from the output of the policy network. In the session, we run this tensor to select an action. We get a set of probabilities, and then we randomly choose from those probabilities to select an action. Here's the main reinforcement learning loop. This is what we talked about earlier, where running the action probability tensor to produce some action probabilities, and then we randomly choose between the action probabilities. Here in the session is where we optimize the policy net. One other note for TRFL usage is the scan discounted sum. This is a convenient function that takes in a sequence of rewards, in our case, a sequence of discount values and an initial value, and produces a discounted sum. We use it in the session here to produce some values, and these values are the discounted reward trajectory. We input the discounted reward trajectory into the policy net, and that completes the reinforced algorithm. Here we have the continuous case of lunar lander. We also have a policy network, but this time instead of producing policy logits, we produce a policy distribution. In this case, because lunar lander has multiple actions, we use a multivariate normal distribution. Here's the distribution, goes into TRFL.policy gradient, and then how we parameterize the policy distribution is with a network for producing the mu value and a network for producing the scale value. And these outputs, mu and scale, they go into the policy distribution. Once again, we have placeholders for action and value, and these are the other parts of the TRFL.policy gradient function. You'll notice that we use a value function network, and we'll go over that next video. We discuss reinforce with baselines. Further resources.